Okay, so welcome back. So hope you got a little bit of a break, and let's go ahead and talk about how to run one-way ANOVA in RStudio and interpret it. Let's get started. In this demo, we'll look at the wellness dataset, and we're trying to examine the answer to this research question. Do self-rated sense of well-being differ based on participants' use of therapy-based coping strategies? And to answer this research question, 199 college students were recruited. You can almost hear the researchers going, we could have used one more for than even 200. And that researcher, of course, is me. And students rated their sense of well-being, which was captured in a continuous variable called well-being. And participants were assigned to one of three conditions based on the type of coping strategies they were using to cope with everyday stress. And here's a list of three conditions. One was related to acceptance and commitment therapy. Second was related to cognitive behavioral therapy. And then the third was just a control condition that did not have any theory-based coping strategies. So the dependent variable is well-being, and it is a continuous variable. An independent variable, which is categorical, is condition. And the hypotheses look like this. And so the null hypothesis would say that there's no mean difference in well-being based on condition, so the three groups. And then the alternate hypothesis would say there was a significant mean difference in well-being based on condition. And so at least the two of the three groups differed from one another in the well-being rating. And so let's take a look at this in RStudio. Now, before we get there though, let's talk about some basic steps related to running a one-way ANOVA. So this is our kind of roadmap, if you will. First of all, you want to run the Levene's test so that you know whether or not the homogeneity of variance assumption is met. And that will help you select how to run your one-way ANOVA. And so we're going to look at two different versions. The first version is a basic version where you can assume homogeneity of variance. The second version is what you would do if you did not have homogeneity of variance. And so there are two different ways to run it based on whether or not the homogeneity of variance assumption was met. Now let's say that you get a significant result for your one-way ANOVA, in which case you want to run the third step, which is to use a post-hoc test and figure out which groups had significant mean differences. And so let's talk about the first step before going over to RStudio. And so the first step is to run the Levene's test. And before in independent samples t-test, we use the var.test in order to run the Levene's test. However, in this instance, when you use one-way ANOVA, you may have multiple groups, not just two. And var.test does not work if you have more than two categories to compare. And so we'll want to run the Levene's test a different way, which is to use a Levene test function in the car package. And so you'd want to install the car package first, and then load it so that you can use it, and then run this Levene test. And we'll look at this in RStudio. But note that for some reason, Levene is not capitalized, and so lowercase Levene test, big, capital T. And then here's the format. Now, from this point forward, I'm going to continue using a similar language as what you saw in regression, which is that y is generally used to designate the dependent variable, which is typically continuous. So y equals dv. And then x is used to indicate independent variable, or IV, which is categorical variable. So when you see me write things down as y and x, then typically that is what I mean. All right. So without further ado, let's hop on over to RStudio. Meet you there. All right, so hello. We are here in RStudio, your good old friend. And you can see that I have already imported the wellness dataset. And you can also take a look at the viewer if you're curious. And I've attached the dataset so that I can use it without referring to it all the time. And I've also started to program the code for Levene's test. And so I've got as far as here, but I haven't yet installed the car package, so I wanted to go through that with you. So let's give this a try. Fingers crossed. My, that was a lot of activity. Now let's see if we can run the library car. Loading required package, car data. Interesting. And so yes, CAR comes with a bunch of data sets you can actually use for demonstration purposes or training purposes. And so I assume that that is what it means. So we have now opened up the CAR package. So now that we've got that loaded, let's try to go for the Levene's test. Now in this instance, we've talked about Levene test, and this is the option that I have shown you in the lecture slides. And the dependent variable is well-being. And then the independent variable, which is a categorical variable, is condition. And there are 3 conditions, as you might remember. And then you can technically ask RStudio to center based on median or the mean. Typically when I use a Levene's test, I use the mean, and so I'm going to leave it as mean. But do know that you can also try to run the Levene's test around the median. So that's very interesting. So it says that in Levene test default, a condition is coarse to factor because it is currently just a string variable. But it recognized that it is a text variable with 3 different levels. I can tell that by looking at the degrees of freedom, but you can see the results of Levene's test here. Now you notice in this output that the p-value is greater than 0.05, in which case you retain the null hypothesis saying that the homogeneity of variance exists. And so now we're going to talk about running a standard one-way ANOVA where the assumption of homogeneity of variance is met. So let's hop on over to PowerPoint. Alright, so let's talk about running your one-way ANOVA. And so it works similarly to regression. And so you would save the following model here, where the y variable is the dependent variable, continuous. And then this time, unlike regression that you might have remembered this from, x, or the independent variable, is categorical. But in any case, you would save this into a model and then run an ANOVA instead of a summary function in order to get the one-way ANOVA output. Now, technically, you can run the summary as well, but ANOVA, I find, is a more user-friendly way of looking at the results. And so this is the basic form of one-way ANOVA. Now, just FYI, what if you didn't meet the homogeneity of variance assumption? So the Levene's test was significant. You had a small p-value. In which case, you can run the one-way.test function. And in this case, you don't actually have to save this as an object. You can just actually run it, where, again, the y equals dv here, and then x equals iv. And then that will give you an adjusted F-statistic you can report. And so if your homogeneity of variance assumption is not met, then go ahead and run this form of ANOVA. So let's hop on over to RStudio. So welcome back to RStudio, and we are getting ready to run the one-way ANOVA. I started taking notes. We're running the regular form that you would run where you have homogeneity of variance assumption met, and you check that using the Levene's test. And so now we're using the LM model again, and I'm saving it this time to an object. I called it well model, but certainly you can call it whatever you like, as long as it doesn't conflict, of course, with things that would confuse RStudio. And so what will go in here? So you might be thinking something like this. And so this would be the model. Well-being is essentially getting regressed on condition. Condition is the independent variable. So you can run that. And then instead of summary, I'm going to ask for an ANOVA. And here it is. Ta-da! So here is our ANOVA table. Now this is very exciting. We will hop on back to PowerPoint in order to interpret this shortly. However, I wanted to just show you as a curiosity item in the console what would happen if you had data where the homogeneity of variance assumption was not met, in which case you would of course run the one-way test. Whoops. So here's one-way test, and then you would regress well-being on condition, essentially. Whoops. And so let's try running the one-way.test, which is what you would run if your homogeneity of variance assumption was not met. Ah, interesting, right? And so you get similar types of output, but in a little bit of a different format. And it looks like this one-way analysis means not assuming covariances, so it tells you what it's doing. And then you can report these statistics. And so let's go over to PowerPoint to talk more about interpreting the ANOVA table. So here we are with our ANOVA table. I've copied and pasted it here. And you will notice that the ANOVA results are given to you in a table where the first row is your IV. And then there'll be degrees of freedom associated with it, sum of squares, mean square, F-statistic, and then the p-value in order. And then the residuals row gives you the information for within group variance or the error. So we've gone over all those terms before when we covered information about ANOVA. But when I see a table like this, really the first thing that I pay attention to is the p-value. I just kind of cheat and go to the p-value because that will tell me whether or not I have a significant model. In this instance, the p-value is greater than 0.05. And so do you reject or retain the null hypothesis? You retain or fail to reject the null hypothesis. And so really it's saying that there's no group difference. Now, how would you write this up in APA style though? And so I've converted it to the APA style writing where you would start with the italicized, capitalized F, and then right next to it is the open parentheses, and then you will put the degrees of freedom, the numerator degrees of freedom here, which is associated with your independent variable, and then the denominator degrees of freedom, which is associated with the residuals row. And so the degrees of freedom come here like this, and so there's comma and then a space, and then the denominator degrees of freedom. And so for your notes, I've written out numerator degrees of freedom, denominator degrees of freedom. Numerator associated with your IV, denominator associated with the residuals row. And then you would write the F value, and then report the P value. And so this is a pretty standard way of reporting statistics in APA style. The only major thing that is different from what you've seen before is that you've got two different degrees of freedom. Now what happens when you have Welch's F? In this case, all the information you need to write up your F-statistic in APA style is given to you in one row with pretty easy to understand information. And so this is all what you would convert and write up in the same style as before, except for that the F-statistic has decimals in their degrees of freedom because of the Welch's correction. And then the numbers will look slightly different, but the results are about the same as before, in that you failed to reject the null hypothesis. But I just want to show you what it would look like if you were to write up Welch's F-statistic. Very similar, just the numbers are replaced by adjusted degrees of freedom and associated statistics. Now, if we come back to our three-step process, in this example, we just stop here by reporting the one-way ANOVA, and we would say that there are no significant mean differences across the groups in the condition variable. And so you would skip the third step of running a post-hoc test. But what if you had a significant result? Now, in the world of hypotheticals, if you had a significant one-way ANOVA result, then you would proceed to the third step of running the post-hoc test. But before we get to specifics, let me share with you a note on post-hoc tests. Now, one thing to know about post-hoc tests in ANOVA is that you have many options to choose from. Now, the researcher would, in real-life context, choose the best test based on their preferences and the nature of the data. Now, this type of decision-making is beyond the scope of this class, and so we're going to use one example which is based on Bonferroni correction. And so I just wanted to let you know that there are many different types of post-hoc tests you can run for ANOVA. We're going to use the one that's based on Bonferroni. And it looks like this. And so you would be running a function called pairwise.t.test, and then in parentheses you would say the dependent variable and then the independent variable, and then include a statement p.adjust.method equals, and then in quotation marks Bonferroni. Now, this is a lot of typing to do, and so you may wish to copy and paste off of the lecture slides or use my lecture code. I'll put it in there for you later on. But this is how you would run the Bonferroni correction. And so remember that y equals dv and x equals your IV. And what it spits out is that it gives you a grid of p-values associated with those pairwise tests or comparisons. And so in this instance, we don't really have this instance, but when you're running this post-hoc test, you should, in theory, have at least one significant p-value somewhere in this grid, because you're running it because there was a significant one-way ANOVA result. In this case, though, I'm just showing you an example here that doesn't have one, just to show you what the grid looks like. But you want to look for portions of the grid where p is less than 0.05 to know which pairs of levels or groups differed significantly from one another. Now let me hop on over to RStudio to explain just a little bit more, and also let me show you a way to display means for each group, which may be useful also in interpreting the differences. So here we are in RStudio again, and I've just kind of written up some notes on what you would do if homogeneity of variance assumption is not met. Now in this case, we're looking at step 3 of running the post-hoc test if ANOVA happened to be significant. So ignore this particular example in real life because we know that there was no significance. But if there was a significant ANOVA, then this would be the type of code that you would run to examine which means differed significantly from one another. So let me show you what it looks like to run that pairwise test based on the Bonferroni correction. And so here is what happens, and they show you the p-values associated with those comparisons. Now, right now, we see no significant p-values here because we know that the ANOVA itself is not significant. I had a lot of trouble in looking through my data. A good example to show you for this kind of thing, part of it is that I used randomization for my condition at one point, and it worked. And so there's no significant difference across many different factors. But let's take a look at maybe one example where it's a little bit harder to see, but we do have a significant ANOVA result. So let's say we wanted to see if students in different years of school differed in the age. And so age is a dependent variable that's continuous, and then year in school was the independent variable. And so let's see if Levene's test. And so I'm going to run stuff here just because this is kind of all hypothetical. But let's say age was a dependent variable, year in school was the independent variable. Levene's test. Again, year was chorus to factor, but there technically, if you look at, say, table year, you will see that there are 4 different classes: freshman, junior, senior, sophomore. A little out of order, again, because it's alphabetized. But anyway, and so we'll do the Welch. So, whoops, age is the dependent variable, and then year is the factor. And then we get a significant result because p-value is very, very small. And so there's some sort of a significant difference, mean difference in age across those 4 different years. Now, where did it really differ is where we want to use the pairwise t-dot test. And so in this case, the dependent variable is age, and then year is the independent variable. And so we would run this to see what the pairwise differences were. Now, so here is a grid that shows you the p-values, and here, all of these are very, very small p-values. So you can see that sophomores and seniors had a mean difference in age, significant mean difference in age. The same was true between sophomores and juniors. They had significant difference in age. Not so much between freshmen and sophomore, and not so much between seniors and juniors, but significant difference between freshmen and both juniors and seniors. And so it's kind of hard to read because the p-values are in scientific notation, but as you know, these are very, very small p-values, and so they're indicating where there were significant differences. And so hope this kind of gives you a feel for what it would look like to do pairwise comparisons. And so look for significant p-values to identify the groups that differed. That is the bottom line. Now, all of this is very nice, but what if you wanted to figure out what the means were, right? Because at this point, we have not really seen a good example of the dependent variable broken down by mean. And when I do post-hoc tests in general, I really want to figure out what the means look like. So I might do the function aggregate. And so let me start with the initial set of variables. And you would say, here's a dependent variable, well-being, and then you would do a by statement. And you want to give the categories by which to break down the the means for well-being, which is condition, using the original variable. So this is x variable. And then give me the means for those. And so essentially it's saying, whoops, take the variable well-being and then break that down by condition and give me the mean. So summarize the means for me. And so if you run that code, you will see that even though it says X, this is actually well-being. So mean for well-being shown for each group within the variable condition. So of course, we can apply that to age and then do that by year to see what the mean ages were by group. Again, a little bit kind of getting me cross-eyed because the groups are organized by alphabetical order, but you can see that the freshmen had a mean age of 18, sophomores 19, so not surprising that they were different, whereas there's a big jump to junior 23 and 25, 24-ish for seniors. And so this is the way to tell what the means look like by group, is to use the aggregate. And I have written down this code for you in the lecture slides as well so that you can keep it for easy reference. All right, so let's talk about what your APA style write-up would look like. And so you already are familiar with how to write the F-statistic from the previous slides. And so you might just explain what you found. And so in this case, participants' self-reported well-being did not differ based on their condition. And then you can just put a comma after your sentence and then append that with the F-statistic write-up like this. Now, the story ends here for this particular example because you did not find a significant effect. If you did have significant effects, then it will be helpful to the reader if you explain where you found significant differences, because that's not automatically apparent. And so I've just written out a sample write-up that you might use to kind of model after if you were to write up post-hoc comparisons. And so in this case, post-hoc comparisons using Bonferroni correction revealed, let's say, this is all hypothetical, this is not true based on what we have from the data, but this is a way in which you can write it up. And so you can give them the mean and the standard deviation for one group that differed from the other, and just mention those group differences so that people can see what groups differed and then in which direction, so which group scored higher or lower. And so again, this is just all hypothetical. This was not true based on the data that we had, but if you had significant results, then here's an example of how to write it up. So here's a summary of one-way ANOVA. And so you would have one continuous variable that serves as a dependent variable, and then you would have one categorical variable that serves as a factor. And this factor can have multiple levels, so not just two like in the independent samples t-test. One-way ANOVA can handle more than two groups to compare. And so what you're doing in the setup is that you're trying to test whether the means of the dependent variable would differ across different levels of the factor. And so essentially, the factor gives you groups of individuals, and then you're comparing whether those groups differ on the means for the dependent variable. And so you would use the F-statistic to test for any potential significant differences. So essentially the question is, are there any group differences? And then you can use the LM function and then use the ANOVA function to get the actual printout of the ANOVA table. And if you do not have homogeneity of variance, then you would use one-way.test in order to get Welch's corrected F. Now, if you happen to have significant results in the one-way ANOVA, then go ahead and run a post-hoc test to figure out where the mean differences were. And so again, the one-way ANOVA gives you a general sense of whether there were any means that were different. It doesn't tell you where those mean differences were. And then you would use a post-hoc test only if you have a significant result for ANOVA. So essentially you have significant group differences in the dependent variable. Then you would use a post-hoc test. And so, drum roll please, it is your turn to run your own analysis. And so here's a research question for you. Does self-reported well-being differ by the participant's year in school? And so the year is that familiar variable where the participants indicated whether they were freshmen, sophomores, juniors, or seniors. So does well-being differ by the year in school? And if so, then where are those differences? How? And so please follow the similar steps as you saw in the lecture and go ahead and give it a try. Hope you enjoy running your one-way ANOVA. So So have a wonderful week. It's been great spending time with you. I hope you enjoyed your foray into the ANOVA land, and I hope you have a great week. Talk to you soon and take care. Bye for now.